Hello and welcome back. This is presentation 7.5. The topic today is sample sizes and confidence intervals. We want to acknowledge the development team of Brad, Spencer, Amanda. Our illustration today involves a sampling in an effort to find an estimate of mean weight of men. And if you can see on the screen here, we're going to take a sample size 41 men, and the sample mean was found to be 173.4 pounds. We're going to assume the standard deviation for the population of all men is 25.2, and we want a 95% confidence interval. Now we know that the central limit theorem says that based on samples of size 41, the sample means will cluster around the population mean, which we don't know. It'll be approximately normally distributed, and the standard deviation is given by sigma over square root of n, which in this case 25.2 square root of 41 is 3.94, and that's called the standard error of our estimate, and that's really the 68% confidence region about the population mean. We need a 95% confidence interval, and as you know, that's associated with a z-score of 1.96 times the standard error, 3.94, gives us the margin of error of 7.72, and as you can see, that is the confidence interval here on the screen. We can be 95% confident that our x bar falls within 7.72 units of the population mean. If we did find an x bar of 173.4, then we simply substitute it into that equation and get the 173.4 plus or minus your margin of error, and that is your confidence interval we see on the screen here. In the lower right we see an idea of what that might be. The red dot is your x bar. Add and subtract 7.72 gives us that interval. If the claims made on the elevator regarding the numbers allowed had a mean of 160.0 pounds, of course this interval suggests that the mean weight of men is above that. So they have to change the signs to lower the limit of people on the elevator. Now we've just gone to another screen here, so this information is coming from the previous screen. We know that for 95% confidence, the z-score is 1.96 times your standard error gives us our margin of error of 7.72 pounds. Now comes the interesting part. On the basis of the information above, how large a sample size n is necessary to find an estimate of the population mean mu with plus or minus 4.0 pounds error with 99% confidence. And look what's happening here. We're looking at the formula above. Your error term is plus or minus 4.0. Your z-score for 99% confidence, 2.575. Your standard error, 25.2 over square root of n. And we need to solve for n here, so we cross multiply, square both sides, and find n is 264. And conclusion then, to find an estimate to within plus or minus 4 pounds of the true population mean with 99% confidence, we must go to a sample size of 264. We just illustrate on the screen here. 264 means this sampling distribution is narrowed significantly so that the standard error is 1.55, and you can figure that out yourself. For 99% confidence, 2.575 times your standard error gives us a margin of error of 4.0. Now look at the general case here. We're just going to duplicate this. Your error is equal to z-score times sigma square root of n. If you cross multiply, solve for n, and this is the general formula for your sample size n for a given level of confidence and a margin of error e. The quick and dirty rule is simply this, that from here we have this equation, and if you want to cut that error in half, we divide by 2 both sides, but you see here the 2 is really square root 4. So in other words, to cut the margin of error by 2, by half, you must pump up the sample size by 4, and if you want to cut it by a third, you must pump up the sample size by 9n. Generally, if you want to cut the error term by 1 over k, you must increase the sample size by k squared times n. And that's the end of 7.2. We ask you to review this once again, take notes, and look at presentation 7.6.